right, class. Welcome back to another Natural Intelligence, the Blueprint for AI lesson. We are going to be discussing in this lesson number 6, the compression algorithm. Your brain learns from prediction errors, not just passive review. So when you generate output and get it wrong, that mismatch triggers deeper encoding. And AI works similarly the same way through loss functions and what we call back propagation. So we're going to break that down in this lesson. But first, a quick recap. The 3 points here we want to recover from the knowledge graph is thinking about the schema theory that we got integrated info encoded in 3 times faster. This is the schema theory introduced to us by Piaget in 1952. And this is where knowledge was organized into interconnected semantic frameworks. And then we also learned about vector embeddings, which allow us to mirror schemas in the math space. Now, with RAG, retrieval augmented generated, mirrors hippocampal retrieval. And then finally, you guys built our fourth tool, a schema graph, where you were able to map new topics onto your existing knowledge. Now, moving on to today's lesson, let's talk about the biological hardware. Now, our mission for this particular course is to generate an error signal through active processing instead of passively reviewing material. You want to force yourself to produce output. In other words, answer, explanation, summary, tutorial, teach. These are things that are forcing you to produce output. The mismatch between your output and reality is what we call the error signal. So if you are making errors, you signal to your brain, hey, I may need to course correct. And that course correction during the retrieval process is actually how we learn. Now, the mechanism has two foundational findings. The generation effect by Slamecka and Graf in 1978. The information you generate yourself is remembered better than information you merely read. So, this is why it's important when you are taking notes or listening to a lecture, you take notes because what you're doing there, you're actually generating notes or generating data, which is recalling, or excuse me, which is requiring, your brain to recall information that is being stored. The other foundation finding is the testing effect by Roediger and Karpicke in 2006. And this is when we were taking on a test on material produces better long-term retention than just simply spending time doing the restudying over and over the same material. And why is that? Well, the reason is generating output forces a prediction, right? As you are starting to speak or think about presenting, you have to sort of think ahead of what you're going to say next. And when that prediction is wrong, the mismatch creates an error signal that triggers targeted re-encoding at the exact point of failure. So take, for example, while I'm speaking to you here on this lesson, sometimes I am thinking about what I'm going to say next, or I'm foreshadowing a little bit inside of my own mind and I'm predicting. And then when I speak, sometimes I may misspeak and I may say the wrong thing. So there's a mismatch in my brain, what I'm trying to predict or what I am predicting I'm going to say versus what happens in reality when the words flow from my thoughts to my mouth and then to this microphone. And so there's a error signal there when there's a mismatch, and you can see me catching myself or saying excuse me or repeating myself. And that's an example of us trying to generate some output using prediction, but that prediction doesn't match the actual output in reality. Now, the problem here, most learners default, right? We default to passive strategies like rereading or highlighting or reviewing the same notes when we're studying. We just study the same thing over and over again and think that we're actually learning the more we look at the same material more frequently. These feel productive, but they generate no error signal. You're simply just rereading or reviewing the information you've already taken in once. And since you don't have that error signal, the brain doesn't know where to update. Now, 50% stat here, Roediger and Karpicke, 2006, found that students who took a recall test after reading retained 50% more at 1 week compared to students who reread the same material for the same duration. Now, let's look at that in a visualization here to make it look a little bit, make more sense to us. So we have this neurofeedback here. And you notice that in stage one of the neurofeedback, you're going to move along this continuum here where you're going to predict. And this is where the brain is generating a thought bubble, right? Where you have that image of a thought bubble hovering over your head. And what's going on is your brain is processing and producing a prediction of what you want to output. And then we go to stage two, where we have a comparison that happens where you're magnifying over a target. And this is happening in stage two. Now, this target, of course, could be the particular material either you're reviewing or the material you're getting ready to present or an exam that you're getting ready to take, but some type of recall that you want to zero in on or focus on. And then in stage three, we encounter the error signal. This is that lightning bolt with a mismatch indicator, which is essentially a signal to your brain that, oh, wait a minute, what I was predicting and what I actually said or what I was able to produce did not align. There was a mismatch there. So this signal, this error signal, gets highlighted in your mind. Your brain takes notes of that. And so what happens after that, your brain says, oh, you know what? That was a mistake. That was an error. So I need to make an update here. And then when we update, what we're actually doing during that update, our brain is strengthening its neural pathway. And this is what leads to that fourth stage or that final stage of updating, leading to retrieval and hardening of the neural pathway. And you continually go through this neural feedback loop, strengthening those pathways each time you try to generate or make an output prediction, and you need to make some type of update that was incorrect. Now, how do those signals work, those error signals? Well, first, the error loop, you have a prediction step where we're going to generate an answer from memory. Then we're going to compare or check against the correct answer. And there we have the error where there's again the mismatch. And then we do the updating. Now, let's compare that as we just saw in the previous slide with our visual. Let's compare that to passive versus active. In passive review, or you can consider this passive studying, you're rereading and highlighting. And it feels productive, but again, there's no error signal generated. Now, with the active generation, this is when you may quiz yourself, or maybe you're writing or rewriting the information and causing yourself to predict or produce output. It may give you the opportunity to make an error while you're explaining or teaching or speaking. It feels very hard, but the error signals generated at every failure point deepen that encoding for you. They deepen that neural pathway. And we learned this result from a desirable difficulty by Bjork in 1994. Here's an example of a visualization just to give you a frame of reference. On the right, we have this passive, sort of very clean, organized desk of study materials. But all you're doing is just flipping through the pages, reading them. Maybe you do some highlighting, but not a lot of generation there, not a lot of potential for error signals. Whereas on the right here, we have an active example where you're making mistakes, you're trying to predict what comes next in the flow, or what comes next in the story, or what comes next in some output that you're predicting. And in that case, right, you realize, oh, I made a mistake. I predicted wrong. I guessed wrong, or I answered incorrectly during a quiz. And that is exactly when you get those error signals requiring your brain to update. So, what's the bridge here? The bridge from the human error signals to the AI, what we call loss functions, are pretty straightforward. So, with the human, we first process information or generate an answer, and we compare the truth. Very simple. That same process in an AI model is what we consider a forward pass and then compare to the label. you're looking at what the expected predicted outcome should be, and you're getting uh, some type of outcome of via that comparison, right? And this was what we call a loss function. Higher loss functions mean more incorrect comparisons, right? So we want to reduce the loss function as much as possible. And then same thing in the human brain, we want to reduce our error signals. Now, the error signal in the human brain, in our natural intelligence, there's a mismatch that gets triggered for encoding or re encoding. And the error signal in the AI intelligence is the loss function computes a gradient. And this is where we have something called gradient descent, where we essentially try to step our way very slowly to the correct answer. And then we have updating on the human side is the synaptic strengthening at failure. So every time we fail, there's an update, and that actually deepens our learning. It deepens that neural pathway. The update portion on AI is through what we call back propagation. And this is where the weights of the parameters get updated, essentially helping the model make better, more accurate predictions with new data coming in. Now, the weaknesses on the human side is that the ego avoids errors, right? We get into a comfort bias where we avoid making errors. Maybe we do not stand up and raise our hand, or raise our hand and stand up to speak in public because we don't want to make the mistake of misspeaking and looking foolish. So our ego prevents us from that opportunity of getting those errors and making those mistakes, and therefore learning in the process. Now, with the AI loss function, the weakness here is that you can overfit to training data. Now, we'll speak more about training data in the process of training models when we get into our AI course. But just know now you could overload, or you could also underload the model with either too much or not enough data. Okay. In other words, not enough opportunities, not enough at bats to try to pass or fail. Now, the axiom here, both brains and neural networks learn from prediction errors, not passive exposure. And the key thing here is that the error is, in fact, the teacher. You learn when you make mistakes. So make a lot of mistakes. Let's take a quick look at the architecture just to visualize those two comparisons to bridge the human or natural intelligence to the neural network. Again, the flow of information is going in from input down to internal prediction for our AI. It will be forward pass. For our human, we're going to do our comparison of what we predicted to what actually happened, or the reality. And in the neural network, you're going to have a comparison of the prediction to the accurate or correct label. And then the error signal side, you'll get an error update that will signal an update. You'll get an error signal on the human side. On the AI side, there'll be a loss gradient. And again, that will cause you to have additional epochs, additional cycles running that model or that training set to try to reduce that loss function as much as possible, getting to the correct or a very high accuracy of predictions. And then finally, that update uh, from the error signal causes our brain to make an update, which then the result is a synaptic strengthening, meaning we deepen our neural pathway or our understanding and learning, which ultimately allows us to retain more information and be able to recall it. Now, then on the AI side, what we do, or what models are trained to do, are to update their weights via back propagation. And we'll learn more about back propagation in the AI course. So, how do we get around this? Let's think about some ways we can use this error signal, um, the error signal strategies, because there's four of them that we can do to use them in our favor. So, number one is going to be to generate before you check. So, write your answers before looking at the source, create the prediction error signal loop. So, again, generating or trying to essentially guess or answer correctly, what you're doing is you're choosing or forcing your brain to produce a prediction, right? When that prediction is not right or correct, you get the error signal. Number two, you want to embrace the struggle. Okay. So desire difficulty. If it's hard, if the retrieval feels hard, that means that there's a potential that you have deeper encoding. So that struggle or the difficulty you see there, it's a feature, not a bug, right? You don't want to be in a position where you're learning things that are easy because you're not truly deepening the neural pathway. Our third strategy is closing the loop. So check your output. This is where we compare against the source immediately. The comparison moment is the learning event. When you try to predict something and you realize you were incorrect and your ego doesn't overtake you and make you ignore that, if you lean into that missed prediction or that incorrect prediction or incorrect outcome, this is where you have that, again, the error signal lighting up in your brain and gives you the opportunity to learn. Then our fourth opportunity here or strategy is going to be spacing the errors, distributing generation attempts over time. So each error at a different interval compounds the effect. And this is why we talk about ways to uh, break down your study regimen or your review of material over a time span so that you're getting more reps and more opportunities to deepen the path. Now, learning about RAG, for example, let's take a topic here. Uh, let's put into action what we just saw. The first step is to generate. So we're going to generate some information and think about what we believe RAG is. So we're just going to say, okay, RAG retrieves data before generating. Okay, we're just going to generate some information or generate some output. And then we're going to compare. We're going to compare uh, what I ingested or the input that I ingested. And here is the opportunity again to check whether or not what I generated is indeed accurate. If it's not accurate or if it's wrong, I'll go to step three and I'll have my error. That error then leads to the re-encoding. The re-encoding phase is indeed what happens when you learn. Okay. So we believed or we perceived that RAG retrieves data before generating, but indeed, RAG retrieves data, then it embeds it before generating. So there's actually a correction here. We were incorrect to begin with. We had an error or a missed embedding step. And this essentially allowed us to update or correct ourselves. And when we did that, when we saw what the correct answer was, even after generating, that gave us the opportunity to re encode or strengthen our learning. Now that we know a little bit about what we're doing with this compression algorithm and how we're using the four strategies, let's think about some of the objectives here. Let's design a generation loop, which is essentially a quiz and output protocol that forces error correction. So you'll generate an answer, you'll compare it to the truth, then you're going to identify the error where you got the answer incorrectly, then re-encode at the failure point. And we'll have two tracks as normal. We'll have our architect track and our builder track. Our architects are going to be designing the generation loop template, where our builders, as normal, will be generating a loop system prompt. Requirements for the architects, you all are going to be generating a template or creating a generation loop template, excuse me, where it must include a generation, closing the source, write your answer from memory only. So this is where, again, you sort of take that practice test without knowing the answers, but you've studied a little bit. Now you want to test your ability to recall the answer. So this is our generation step. And then you're going to compare. You're going to go back and look at that quiz, grade yourself. How well did you make the generations? Did you predict? Then you're going to diagnose, identify the exact error. Which questions were incorrect? Did you have a problem with some of the math material? Did you have a problem with maybe some of the writing material? Did you have problems on certain concepts, certain deeper technical concepts or more abstract concepts? Right? So diagnose where the error happened, and then you'll finally be able to restudy only those particular failure points where those types of questions tripped you up. You don't need to restudy everything. You just need to be able to restudy where you are not able to accurately generate the answer. Okay. This is again targeted, not full reread. This is important because you need to reserve as much of your mental and cognitive resources as possible. Then you want to retest. You're going to wait 24 hours and then generate again. This is incorporating spaced repetition, spaced retrieval here, so that you don't repeat, or you're going to repeat until you have error free, or you are error free. Now, the builders, you guys are going to build a prompt that will generate some quiz questions from your large language model. Choose the language model of your choice. You can use Sonnet from Claude or Opus from Claude, or maybe you're using GPT from OpenAI, or maybe even going over to Gemini from Google. Choose your large language model for generating this prompt. Then you'll evaluate user answers and identify specific errors, what's missing, what's wrong, what's incomplete. And again, you can use the large language model to evaluate those answers for you. You don't have to do it by hand. And then number three, you're going to provide targeted review, focusing only on failure points. So again, only target your restudying on the things you got incorrect. Okay. And then finally, schedule a retest at spaced intervals. You can bake this into the logic of the system prompt so that you can get a very nice calendar and schedule defined by your large language model. And this will, again, build onto our stack of what we've been learning. We have our high salience topic, our chunking ability. We now know how to use text to visual for dual channels. We previously learned about the schema graph, and now we have our generation loop. So we're again just stacking tools on to make ourselves a very optimal learning. Excuse me. All right, that wraps it up for today's lesson. Let's recap what we learned today, what to remember. So first things up is that your brain learns from prediction errors, not passive review. The error signal is the teacher. You want to make mistakes, not just take information in, review it, and not try to generate or regenerate it. Number two, the testing effect. Retrieval produces 50% better retention than restudying alone. So again, it's that ability to retrieve what you've studied or what you've ingested, which is far better than just ingesting the information, reading or viewing or listening. Number three, loss functions, error signals in math. Backpropagation equals brain's error correction pathways in silicon. So two different ways to mitigate some of these error signals, right, or at least capture them, but they're both equally important and part of the workflow for learning. Now, four, desired difficulty. If it feels easy, you're probably not learning. Just realize that. So struggle drives in coding. Struggle gives you the opportunity to make mistakes. Again, those mistakes give your brain the opportunity to make updates. As you make updates, you deepen your neural pathway. And then finally, just a review of our stack here. We know that we now have 6 different items, our tools in our tool belt to help us learn. And we'll be moving on to the 7th tool, which is our query function, where we'll retrieve practice space repetition in chain of thought. So we'll have retrieval practice, space repetition in chain of thought. In the next lesson, the query function. So until that, practice your build objective. Make sure that when you're learning, you're making mistakes and that it's not too easy for you. And really just try to test yourself as much as possible. Push yourself beyond the limits. This is where you'll actually be growing, not just as a human, but also as a naturally intelligent human, which is ultimately what we need to be able to combat AI from replacing us, right? Thank you so much for your time. I enjoy serving you. If you enjoyed the video, please do subscribe. Make sure you stick around for new classes that are coming up, new lessons. Again, we're building the foundation for our natural intelligence before we jump into artificial intelligence, because ultimately we have what we have, and that's our brains. So we need to learn how to use our brains to its optimal ability before we start even considering building an artificial one. My name's Norm. Thank you so much for the time, and see you in the next class. Class is dismissed.